We have a midterm coming a week from Tuesday. Yes, this semester's just flying by. Right? That's what happens when you're having fun, right? Anything we do today or before could be on the midterm. What we do next week will not. So you can kind of draw a line there. If you haven't seen it online, I posted kind of a short list of things you should be able to do for the midterm. If you have questions about it, you can bring them next week or this week. Today, we're going to talk about something called a relation and then also a function. Let's just start with, someone tell me, outside of math class, if I said, here's a relation. Give me an example of what that would mean. Or a relationship. What does that mean? Okay, connection. Right? Can you give me an example? Two objects relating to each other. Yeah. Or they could relate to themselves in a certain way that other things also relate. Right? Like I could be Blanca's teacher and I could be Tina's teacher, right? Well, that's three objects relating two ways, right? Yeah. So in math, we take this idea and we make it extremely abstract. By that I mean, relation can be a relation between any two groups of things that we would call sets. So we could have a set of letters, set of numbers, set of people, set of eye color, and we can have connections between them. So, just as a simple example, here I have like a set of numbers and another set of numbers, and I could have some connection between them. 1 goes to 4, 2 goes to 5, 3 goes to 6. Again, this could be, the set could be people, and this could be their eye color. Right? Now, it's perfectly okay for each of these to go to the same thing, right? Right? Like we might be specifying categorizing animals, right? And so I got my cat Henry and my cat Lola and my cat Cubby. They're all cats, right? That's the connection. They're all cats. We also can have a relation where one item can be connected to many others. Like if you have brothers and sisters, say your mother has a child, this could be your mother, and this could be you and your sister and your brother. So a relation is very general, can be applied to all sorts of things. Can anybody think of a relation that we can express mathematically, but from the real world? Anyone? What comes to mind? What do you think of that I haven't said already? I mean, it's pretty easy once you get used to it. Like, students in this room to their, right, some are freshmen, sophomores, juniors, right? That's a relation. What else? Things we bought on eBay. Scam emails we got from some scammer. I mean, you know, it's very general, right? Okay, so that's what a relation is. Sometimes we'll use the term a mapping. Mapping meaning, you know, kind of these arrows or these connections. Now here in math we end up with some very specific names. The things we're connecting from that set is called the domain. So you take all the things that we might connect from in some particular relation, and that's what we call the domain. It's a set, just a collection of objects. They don't even have to be particularly uniform, right? I mean, you could be one Fred blue. You know, sets are very general. The relation might not make a lot of sense. It can just be one group connected to another with arrows. Usually we're interested in things that somehow make sense, and we'll come up with some examples in a minute. Now, there's a particular kind of relation that we're very interested in math, which is called a function. And the math term function does not equate very well with, you know, just the English term function. Function could be, well, my function is to try and teach. Your function is to try and learn. You know, it's not the same thing. But a function is a relation with a particular property, which is that each element, oh, I'm sorry, I didn't finish what I was saying here before. My apologies. This set, the group of things we connect to, this has a name too. Does anyone know this name? Anyone run into this? Okay, this is called the range. Like if I have some relation and connects to a bunch of things, I might say it connects to a range of things, right? The range. Okay, so the thing about a function is that each element in the domain, well, we'll just do something simple, connects to just one element in the range, right? So here's an example. Well, here's an example of something that's not a function, right? One connects to one and one connects to two. Not a function. We'll talk about this some more, but that's the key element to make it a function. Each element in the domain just goes to one element in the range. Now, they can all go to the same element. There's nothing wrong with this. This is still a function. Uh, 1, 2, and 3 go to 1. That's fine. All right. Okay, so that's one way to think of a function. Yes?
I just have a question. So, like, when you're doing the arrows, does that mean they're, like, similar to each other?
No. It doesn't mean they're similar. It means as part of our function, we're connecting them.
Oh, it's like...
Let me give you an example of something, right? You walk into a store, right? And I'm just going to... There are things for sale. I'm just going to label them A, B, and C. But they really, bubble gum, milk, whatever, right? These all map to a range of prices, what you have to pay for. Nothing, bubble gum and 50 cents are not the same thing. They're just connected.
Because you have to pay for it.
Well, you should pay for it, yes. Not everybody thinks that, but yes, you should. Okay, so here's a different way to think about a function, or a relation for that matter. You can think of it as a bunch of what we call ordered pairs. A pair, it's just two items. Here we have 1, 1, 2, 1, 3, 1. I'm describing the same function here and here. The order is important because the first item is the domain and the second is the range. So if I just take this collection of ordered pairs, they're equivalent to this same function I have with arrows. Another way to think of a function. Think of some kind of machine. It has some kind of input. Could be a computer, but it, could be like, I don't know, you could put like some kind of liquid plastic in and out comes, I don't know, little plasticky dinosaurs, right? But the rule for this machine is, if you put something in, you get something out. If you put the same thing in, you always get the same thing out. Now, I guess if you think of it like one of those candy vending machines, right? That have a place where you put in money. And if you put in the same amount of money and push the same button, hopefully the same candy comes out, unless it gets stuck, right? And then you have to knock it over, right? So that's another way to think of a function. One input, you get an output. You never get a different output out, because that would be like, having one go to different numbers. It wouldn't be a function. Well, now to connect this a little better with math, the input could be a number, and what this machine could be is a formula. Like, we could say x plus 1, where x is our input. So if we put in 1, we get 2, right? If we put in 2, we get 3, so forth. Or some other, complicated formula. Again, the inputs are called, the things we can input are called the domain, and the things that we get out are called the range. All right, now thinking more about mathematics, the input is sometimes called the independent variable. And as we have this function, I'm going to remove the word machine and put function. And we get to put in whatever we want. All right? That's what makes it independent. But the output, once we put the input in, the output is fixed. So the output is sometimes called the dependent variable. Now, at this point, this may seem like I've spent a lot of effort to describe something in very vague terms, but you're probably used to this. You're probably used to an independent variable called x and a dependent variable called y. And you've probably seen this many times. You've probably seen, y equals 3x plus 4. That is to say y, well, that is to say this describes a function. Now, actually by itself it's not really a function yet. To actually say what our domain is. Right? Our domain could be all the real numbers. Or a domain could be just the integers. Or it could, we could just specify it's just the numbers 1, 2, and 3. All right, that could be our domain. Now, once we picked our domain, if you just stuff each one of these in, or all the real numbers, you'll get out, you'll see what the range is. Okay. This is, sometimes what's hard about math is not that the concept itself isn't that hard. It's kind of simple, but it's just so general and abstract that we're not used to, not everyone's used to, thinking in those terms. Like when you walk outside, you see buildings and people, but you don't think in terms of creatures of the universe or, movements like molecules. People are bouncing around like most people don't think in very general terms. But in mathematics, we're always doing that. We're taking some specific idea that we're familiar with, and then we kind of expand it and generalize it to apply to whatever is useful. Function is a very useful idea in mathematics. Okay. I want to familiarize you a little bit with some notation here. I'm focusing in a little more on mathematics now. When we talk about a function, we often will write it and we'll use a curly f. So this says y is a function of x. There's some formula I haven't specified. It could be a formula, or it could just be a mapping, or you could think of it as some kind of number machine. But if I put in an x, I'll get out a y. And this is very common. Sometimes we'll just write the f. Now, often when we're talking about functions, we don't actually say what the domain is or what the range is. You just have to kind of guess. And in general, the right guess is it's the biggest set that would work. So if I say f of x is x squared, well, what numbers can I plug in here? I mean, for us, it's just all the real numbers. But if, on the other hand, if I said f of x equals the square root of x, what about that? If I don't tell you what the domain is, I just say, I've got this function. What's the domain of this function? Think about that for a second. Any ideas? I mean, it won't help to kind of enumerate. Like, you could say, well, 1, oh, that works. 4, that works. 2, yeah, square root of 2, that's a number, right? It'd take too long. You have to think about it. What are my limitations here? What do we know about the square root? How about the square root of negative 3? What's that? You can't, if we're just going to deal with real numbers, we can't do that, can we? How about 0? Does that work? Yeah, 0 works. Square root of 0 is 0, right? So the domain here, even though I haven't specified it, this is a way to specify the domain, is x greater than or equal to 0. Here I could say x, and I'm going to use a little math notation you might not be familiar with. This means is a member of the set, and then we have a name for the real numbers. It's this kind of fancy looking r. So this is just saying the function x squared, the domain is all real numbers. Now, what about the range? I might write it this way. What kind of numbers can I get out? I can put in any real number. What kind of number can I get out of x squared? Can I get 0 out? How can I get 0 out of x squared? You plug in 0, yeah. So 0 is going to be in the range. What about 4? Can I plug something into x that will give me 4? 2, okay. Pretty much any positive number. How about minus 3 or minus 4? Is there something I can plug in to get minus 4? No. Okay. So the range is x is greater than or equal to 0. How about this guy? Square root of x. What kind of numbers can I get out of the square root of x? It's exactly the same. Okay. Gonna put this aside for a second. I know you've seen, we looked at graphs last time. I just want to take a look at what the graphs of these look like, because maybe that'll give us a feel for this domain and range thing. If I were to graph f of x equals x squared, you might have run into this before. It's a parabola, right? In this direction it goes up, this direction it goes up. So the domain is these x values that I can plug in. I can find some point on the line. It's all real numbers, right? I can go in this direction or this direction. It's all the x values. But the y values, right? In other words, if I draw kind of horizontal lines, this is my y-axis. Well, what do you see? There are only y values above 0. I mean, right here at 0, you have 0, 0. So you can just look at a graph and kind of see what the domain and range are. I'm going to graph the square root of x. It just kind of looks like this. I can't put in x values down here, negative values, because we can't find the square root of a negative number. And all the values, they go up. So this is just a graphical way of looking at the domain and range of a function. There's one more thing I want to show you about looking at the graph of something. So I don't know if you've seen this. Well, I'm sure you've seen a circle before. This is a circle, has an equation. Anybody run into the equation of a circle? You run into it? Do you remember it? No. Okay. Equation of a circle, x squared plus y squared equals, well, the radius squared, but we'll just say 1 for now. So we look at this and we want to say, is this a function? Well, if I try and solve for y is equal to plus or minus the square root of r squared minus x squared. Plus or minus. I mean, I could get a point here, and I could get a point down here. Whenever I have a point here, I have a point here. If I have a positive, I'm going to get the negative will also be on this curve. So that means for each x, there could be 2 y's, which means it's not a function. But graphically, we have a very simple way of looking at that. It's called the vertical line test. And the idea is you look at your graph. I wish I had a ruler. Well, here. A very short ruler. And you kind of like look at vertical lines. And if a vertical line goes through 2 points, it's not a function. All right? You don't have to have a point, like out here. There's nothing. That's okay. That just tells me this is my domain. Those are my possible x's. And my range, again, is these y values, which for a circle, it's also from positive 1 to minus 1. All right. Just want to see how we're doing here. Okay, there are other ways to describe a function. You can use words. We'll be using words, but so here's an example of a function. The function which maps each student ID at USF to that student. You all have a student ID, right? You've all memorized it, right? No, I haven't either. I have an ID. I haven't memorized it. But hopefully, your number is unique to you, right? It'd be bad if two of you had the same number. It'd also be bad if you had two numbers. Well, that wouldn't be as bad. So that's one way. You can just state something. The function that maps A to B. You can list in a table. This is a perfectly good way to describe a function. I'll label it. Here's my x, here's my f of x. So I'm just going to use numbers here. So 1 goes to 3, 2 goes to 9, 3 goes to 27. Now, if you're looking carefully, you might see a pattern, but there doesn't have to be a pattern. If there is a pattern, well, maybe you can describe it using a formula. Does anyone see what the formula here is? What do I do to get 3 from 1 that allows me to get 9 from 2 and 27 from 3? Anyone? Let's see, 1 would be, oh no, okay. I think you're really close because you got the number 3 in there. Let's just try switching around. Like that? Is that what you were thinking, maybe? Yeah. 1 goes to 3, 2 goes to 9, yeah. But you don't need that. It doesn't have to do that. We will have functions where we can describe them with a formula. We'll have functions which will just have a table. If you do some kind of, sure, there are people here who are going to do something in the social sciences. You're going to collect data, right? So, I'm just making stuff up. You give people a questionnaire and you as to how psychotic they are, right? So, person in, psychotic profile out, right? That's a function, right? And you can't really, well, you might look for a pattern, like, short people are crazier, or, maybe not, probably not. But, that's what sociologists do a lot of it. They look for patterns that, okay, I just going to say it's nothing to do with math. It's just has to do with statistics. If any of you guys are going to take statistics. So I was reading the statistics book, and it says, it's funny, there's a correlation in Philadelphia between crime and ice cream sales. What? I mean, like if you study how much crime there is in each month and how many ice cream sales there are, one goes up, the other goes up. And isn't that weird? I think it sounds weird. But the answer to the question is, well, of course, they both go up in the summer when it gets hot, right? There's no, like criminals are not. You have to be careful in statistics about connections. That's the message. But we're not learning statistics today. Okay. There are other kinds of tables that these are very specific, right? But you could have a table that's maybe more generic in a way, covers more ground. You're selling, okay, this is real. Price of a first class U.S. letter. For those of you who are unfamiliar, back in the dark ages when dinosaurs roamed the earth, we used to communicate by writing stuff on paper, shoving it in an envelope, putting a stamp on it, and giving it to the post office. We didn't have email. We had the phone, but that was expensive back then. We actually had to think about, hi, Mom. Okay, I got to get off the phone. I can't afford this. I'm not kidding. It was true. I mean, I remember 40 years ago, my grandfather used to call his cousins in England, who he hadn't seen in a long time. It's like $5 a minute. And now, put inflation, it's probably like $25 a minute. Can you imagine? All right. So, back to the letters. So, ounces, and then the price. So, less than or equal to 1 ounce, 49 cents. Greater than 1 ounce, but less than 2, it's 70 cents. And then actually it goes, it starts at 49 cents and then you add, 21 cents for each additional. So less than 2, greater than 2, but less than or equal to 3, 91 cents. And so forth. So there's other ways to describe a function. Here's another way to describe a function that I think you're going to be familiar with. So here we have a circle again, and we want to know the area of the circle. Pi r squared, you recall that, the area of the circle? This is a function. What's the domain of this function? I mean, I could just, yes. Well, the members of the domain are radii, yes. But I actually want to know what the extent of it is. What possible radii could I plug into this?
Pi.
I could put pi in, yes, that's one member of the domain. I could put 3 also, or 7. How about -2? Who here has seen a circle with radius -2? Have you ever seen a circle with 0 radius? No. Actually, how about half? That works.
So the number closest to 0 on the positive side.
How about that? Can't be 0, just has to be greater. That's the domain. See, look at that. It's not complicated. It's just if you haven't seen it before, it's not obvious.
So that just make sure the radius with that part means that it's not 0, it's not equal to 0, but everything higher but 0.
Yes.
Right?
Yes. Yeah. Sorry. I mean, so greater than. Greater than or equal. All right. Equal, of course, less than or equal to. Yeah, okay. Okay, so those are some, common ways to describe a function. Okay, now we're going to get into some mechanics here that tricky at first until you learn the trick. I've got a function. I think I want a new pen. Oh. Now, I can specify the domain of a function. I could say, this is the rule, but the domain is numbers from 6 to 7. I could, and that's a function. If I give you a different domain, like 7 to 8, that's also a function, but it's a different function. But we need a convention for what happens, what's the domain if I don't tell you what it is? And again, the rule is it's the biggest set that works. So the question here is, what's the domain of this function? I mean, what is the largest set of numbers we can use? The largest set of numbers we can put in here. Anyone have any thoughts? Yes, Kate? That's a good starting point. All real numbers. But there are a few real numbers that won't work. Anyone see a number that won't work? What about 0? You can't divide by 0, right? So real numbers, but we'll say x not equal to 0, comma, what else? Is there anything else I can't use? Yeah, what about 1? If you plug in 1, you're dividing by 0. So x not equal to 1. Okay, that's the domain. All real numbers except 0 and 1. All right. Let's try another one. I'm just going to use this letter because sometimes we're already using F for something, so the next letter we'll use for a function will be G. It doesn't stand for function, but we'll do that. So how about this function? Square root of 9 minus x squared. I want to know what the domain of that is. Again. Nobody? I mean, just, how about guess and check, right? How about 0? 9 minus 0 squared. 9 square root of 3. Oh, yeah, okay. So zeros, that works. 1. 9 minus 1 is 8 squared root of 8. That's okay. 2. Well, that's square root of 5. Yeah, it works. How about 3? Well, that's 9 minus 9 is 0, right? Right. So that's good, yeah. 3 works. How about 4? 9 minus 16 minus 5, square root of minus 5. Right? So 4 is not in the domain. Okay, so we run out of room at 3, don't we? Right? So we know 0 to 3 are in the domain. Anything else? How about minus 1? 9 minus 1 squared. That's 9 minus 1 square root of 8. Oh, that works too. Right, can you see where this is going? 0 to minus 3 also works. Right? We can write this. This is, I don't know if you've seen this before, interval notation. This just means all the numbers from -3 to 3. Or you could write this, x is less than or equal to 3, greater than or equal to minus 3. It's confusing because we also use parentheses to mean like an x and y point, but we can use it to mean an interval. But here it's the same, except instead of less than or equal to, it's just less than. In other words, we don't include minus 3, but everything from minus 3 to right before 3. It's just something, a little tidbit. Okay. We don't have much time. I have just a couple more things. I think we already talked about vertical line test. Okay, here's an example. I think we already did this example. Vertical line test will tell you if it's a function or not. Whatever this guy is, f of x, right? He passes. Passes the vertical line. Circle? Nope. You just need 1. So we talked about that. Last topic, I'm going to probably run over a minute, is the topic is evaluating a function. We've been doing that, so it shouldn't be that confusing. Let's just use this one here. If I wrote f of 3, what do I mean by that? I want to evaluate the function at 3. You just plug in 3 for x. Very good. Now you have to do a little math. All right, 1/6. If I told you that this function had a range of 5, 6, and 7, I'm going to steal 30 more seconds of your time. How would I find the range? Well, you just evaluate each one of these. 1 over times 4. 1 over 6 times 5. And 1 over 7 times 6. So that's another way to evaluate the range. You just have a fixed number of items. You can just plug them in. Okay, that's it for today. Thank you.